Okay, so density is abbreviated by the Greek letter rho. It looks like a italic P. Describes the mass of a specific volume of a substance. So density equals mass over volume. Measured in kilograms per cubic meter. And density, now we're covering this again just because we're going to look at how temperature affects this. So if you increase the temperature, your density will decrease. Decrease temperature, your density will increase, so your pressure will increase. So in low density, plane must move faster to achieve the same airspeed because it's not pulling the mass through to make that pull. Low station pressure and high temperatures produce low density. So if you got low station pressure, you're going to have, it's going to be a low pressure anyway. So low pressure, obviously you think, okay, it's less dense because it's low pressure. And then if you increase that temperature, you're going to have even lower pressure because you just decrease the density on that, over that station. So just be aware of like how temperature affects density. If you're forecasting for the lowest pressure at that station for an aircraft that comes in and get a weather brief, then you have to take in the temperature increase throughout the day or temperature decrease throughout the day. If you take frontal passage and the temperature starts to decrease, now you know your temperature is going to go down, so you want to, your minimum pressure that you forecast is going to be a little bit higher than you normally would on a standard atmosphere because you're bringing in a colder air. So now your temperature is going to increase, your density is going to increase, your pressure is going to increase. So all right, water is matter. Matter is made up of three main phases. Pretty much everything we look at in the order of increasing energy state: solid, liquid, and gas. So when we say increasing energy state, we're looking at solid. It's cold, it's frozen, it's not moving around very much, so it has the lowest energy. Once it goes to a liquid, starts to melt, now water will run around, it will move, so it has a little bit higher energy, and then a gas will just kind of float away and move. You can move gas a lot easier than you can water, so now you have a higher energy state. Matter, which has a temperature below its melting point, will tend to remain as a solid. So if it doesn't hit its melting point, it can't melt, so it's going to remain as a solid. It's going to stay frozen. Matter with the temperature above its boiling point, it's going to change to a gaseous state, so it's going to start to evaporate. Once you hit that boiling point, then you start seeing the steam. Liquid does not need to reach its boiling point to change to a gas, so you can have water that's just below boiling temperature, say just below 100 degrees Celsius, and it will still change to a gas. Now, like we said, remember that was from the pressure. If you have a higher atmospheric pressure, your boiling water, it will boil faster because of the higher pressure. So it doesn't have to reach 100 degrees. There are always individual molecules that are spontaneously in a high energy state and will change to a gas. So these molecules are bouncing around each other. They're getting faster and faster. They're bouncing off. The temperatures increase, and some of them are always in a higher energy state, and then they'll jump into the gaseous state even faster. So, and that process is obviously known as evaporation. There are several different measurements for moisture used in meteorology. So you're looking at water, grams or kilograms, and mixing ratio. Saturation mixing ratio. Relative humidity is in percent. Dewpoint temperature is T sub D. Dewpoint depression, like we said on them charts we were looking at where the black dots were, that is dewpoint depression, is the difference between the temperature and the dew point. Wet bulb temperature and virtual temperature. So we'll cover these here in just a second. All right, mixing ratio is the ratio of mass of water vapor to the mass of dry air in a fixed volume. So how much water vapor, if you take a sample of air and you measure the water vapor in that air and compare that to the mass of the dry air in a fixed volume, you get your mixing ratio. So if you have 50% and 50%, obviously it's 50% mixing ratio. 70-30, what is the mixing ratio? How much of that air is moist and how much of it is dry? The greater the mixture ratio, the more water contained in a given volume of air. So obviously the more water you got, the higher the mixture ratio. Kind of makes sense. Alright, saturation mixing ratio represents the maximum possible mixing ratio for a given partial of air. So if you take that moisture all the way up in that, then you got it's saturated. What's the saturated mixing ratio? So if the mixing ratio reaches this volume, the air is considered to be saturated, and water vapor must condense into liquid droplets on or ice crystals if suitable condensation nuclei are present. So largely a function of air temperature. All right, so if you take your saturation mix ratio, you once that air rises, cools, it rises, expands, molecules aren't going to hit each other because they're getting further apart, so it cools. Then it cools to the dew point, starts to condense, but it has to have something to condense to. It has to have CCN, the condensation nuclei, to stick to. Otherwise, it can't condense. There has to be some foreign matter in the air, dust, dirt, pollution, whatever it is. It has to be something in the air to create those clouds. Relative humidity, relationship between the mixing ratio and the saturation mixing ratio. So the ratio equal to water or water saturation. If the air cools, it will eventually reach the point where water saturation falls to water. Relative humidity is 100%. I have W sub S. Okay, so if air cools, it will eventually reach the point where W sub S falls to W. Relative humidity is 100%. Dewpoint temperature. Temperature at which saturation will occur if air is cooled. Okay, so we talked about that. The air rises, expands, cools, condenses. Then it will reach saturation. Water vapor, gas, will change to a liquid form if suitable nuclei is present. You have to have something to condense to. Proportional to the amount of water vapor in the air. So your dew point temperature is proportional. So if the more moisture you have in the air, the higher the dew point temperature. That's directly proportional. Indicates absolute, the actual moisture. So if your dew point temperature is 45 degrees, your temperature is 48 degrees, you're pretty much 90 some percent, saturated. So the dew point temperature indicates the absolute moisture in the air. So the higher your dew point, the more saturated that air is. So in weather, most of your storm chasers, what they're looking for severe weather, is dew points in the 60s or higher. So 60 degrees, 61, higher. Once they hits that 60 mark, that's their magic number. Then they're looking at weather stations as they plot their station plots out every hour to see, send their weather observations out to see where the higher dew points are, so they can try to pinpoint where that severe weather is going to be, and maybe possibly a location of a tornado or something. Dewpoint depression is the difference between air temperature and the dew point temperature. We talked about this on the charts. We'll go back to the chart and look at it one more time. So the lower the value, the closer the air is to saturation, and the higher the relative humidity. The dew point depression of less than 5 degrees at a given level of the atmosphere is suitable for formation of clouds. Okay, so like we said, the difference was 5 degrees or less. If we go back to our charts, right here, 5 degrees, that's the minimum you need for the difference between the temperature and the dew point. So your dew point temperature would be 16 degrees. So 16 plus 5, 21. So your dew point is 16 degrees. You have a dew point depression of 5. There's your difference. That's the minimum you need. If there's condensation nuclei present, then you can form clouds at this level. Now, this is 850 millibars, approximately 5,000 feet. So you could pretty much say, yeah, there are clouds at 5,000 feet over Arkansas, over Georgia. I don't have this thing bumped all the way up. Let me get it. Replot some of these, maybe give me a little bit more station plots here. Okay, so pretty much the whole southeast, all the way down to Florida, that's all saturated. There's clouds pretty much covering that whole area. You can go to look at a satellite, verify that, and then over Virginia, West Virginia, Pennsylvania, you can pretty much say that's saturated also. And then we obviously, where we see the rain, it's saturated, but you have Dewpoint's Dewpoint Depression of 10 here, but like you could be moisture on the surface, moisture in the upper levels, but your Dewpoint Depression at 5,000 feet is a 10, so you're pretty much dry in those lower levels right at 5,000. So anytime you see rain and you've got a dry station with a Dewpoint Depression of over 5, 6 or higher, then you can still have rain because your Dewpoint Depression on the surface is 5 or less, or Dewpoint Depression at 1,000 feet or whatever. So I overlay these on radar, so it kind of makes it look a little more confusing, but it's really not. If you throw it on the white chart, then you can definitely see it, say, okay, there's no moisture there. If I want to look at cloud heights, forecast cloud heights, I can come up to my charts, 5,000 feet, 5, 10, like 18,000, 30,000. You can go 400 millibars, 23,000 feet, and then just kind of see where your moisture is and where your clouds are going to be, kind of the levels of your clouds. Well, these are every 12 hours, these upper level charts, so you got to kind of take that with a grain of salt too. So, but if this pressure system is moving to the east, and then you can say that moisture area is moving with it, then you can say, okay, these clouds are starting to come in. The clouds are reporting the heights of the clouds over here at 3,000 feet. My clouds are at 10,000 feet. I can pretty much say my ceiling is going to drop if it's a ceiling, but we'll cover all that in observations. All right, so 5 or less. Dewpoint Depression 5 or less. The wet bulb temperature is the lowest temperature air can be cooled by evaporation. If you evaporate all the water in the air, how cool can that air get? So it's measured by using a wet bulb thermometer. You put a wick over a thermometer. You get it wet. You sling it. We had a sling psychrometer we would actually whip around. But you put that into the you measure the temperature off of that with a wet wick over the temperature, over the thermometer, and then whatever that lowest measured temperature was. That's your wet bulb. And then it always lies between the temperature and the dew point. So you have a temperature of 80, dew point of 60. You're going to be somewhere in between there is going to be your wet bulb. That's the furthest it's going to be allowed to cool by evaporation. Somewhere in between them two numbers. Can never go below. Can never go above the temperature. Virtual temperature is the expression of temperature that takes into account the density of water vapor. So how dense is that water vapor in the air? Water vapor is over 1/3 less dense than dry air. So adding it to dry air reduces density. So if you add water vapor to a dry air mass, then you're going to reduce the density. You're going to intensify that low pressure system. That low is going to deepen, and it can actually cause more significant weather. So simply the temperature of the hypothetical mass of dry air, so it's a hypothetical, whose density equals of a sample containing water vapor. All right, so the formula is T sub V equals T, which is temperature, W over 6. Increasing moisture or dew point, the virtual temperature will be several degrees higher than ambient air temperature. This increases the buoyancy of the air. So, okay, the way to think of this, like, so dry air holds more moisture than cold air. Cold air evaporates moisture. So like your air conditioning, it takes the air out of your house, pulls the moisture out of it, and replaces it with cooler air. That evaporation is a cooling process. So it cools that air, puts it back into the house. So now you have a drier air mass. So cold, dry air. Warm air holds more moisture. So when it's warm and muggy in your house, that's what the air conditioning is doing. It's pulling that warm, muggy air out, taking the moisture out of it, sending it back through evaporative cooling, and then sending it back to you. So that's the best way to describe it. Even in your car, you have an evaporator. It's under your dash. So it pulls that air out of that car, pushes that through that evaporator, and then it evaporates the moisture out of it and brings a colder, drier air back into the car so you can feel the air conditioning, so it feels cooler. Change of the state. We mentioned this before with the different energy levels. Solid is the lowest energy, liquid is the middle, gas is the highest energy. So if you go from, typically you'll go from a solid to, if you're melting, you go to a liquid, then to a gas for evaporation. You go from a gas, condensate, the air rises, cools, condenses into a liquid, and then that cloud pushes up, or the moisture pushes up above the freezing level. Now you create ice crystals in the clouds. So like, those high clouds, cirrus clouds, are mostly ice crystals because they're above the freezing level. Now, you can go straight from a solid to a gas, and that would be sublimation. A perfect example of that would be dry ice. So dry ice is ice evaporating. Deposition is taking that gas vapor and put it straight back to a solid. Now, it has to still condense on something as a solid. It just skips the liquid state. It condenses on I'm gonna kind of show my age here, but the old icebox freezers, or the old freezers with you had to unplug them every once in a while or bust the ice out of them. They would build up that ice, or the ice tray, the metal ice tray. They actually had metal ice trays back in the day. You would get that white foamy looking ice that builds up on inside your freezer or on those ice trays, and that is like a rime ice. That is deposition. That gas just basically condenses and freezes on contact right onto the metal. So then that's what creates that big white puffy looking snow ice all over your inside your freezer, which I don't know, you may know what I'm talking about, may not there, but maybe you got a picture of it. Coriolis force is an apparent force that acts on objects moving across the Earth's sphere. Occurs because of the change of the angular velocity with latitude. So the Earth is round. The further you move north, higher the latitude, the higher the force of Coriolis force. That's it becomes more noticeable. Produces a rightward deflection on an air partial in the northern hemisphere. It will be a leftward deflection in the southern hemisphere. Magnitude is directly proportional to velocity. So how fast that partial is moving. Faster it's moving, the more deflection you got. So here's an example, like a moving merry-go-round, path of the ball. If you just rolled that ball off that merry-go-round, it's just going to curve to the right. And if you have a camera, this is a camera moving around, moving with the merry-go-round. If you have a stationary camera, you're just going to see that as a straight line. I don't know if that picture helps at all, but the thing you remember about Coriolis force, it deflects to the right in the northern hemisphere. It is a force. It fights against pressure gradient force. There's so much that goes on this stuff. Friction, pressure gradient force, and Coriolis force, and then they start fighting against each other. Like I said, by the time you figure it out, the wind's already blown and that air partial's already moved. So it's just trying to understand, get the basic principles, that in the northern hemisphere, an air partial will curve to the right. Alright, Coriolis force equals FV. F is 0 at the equator and increases with latitude. Coriolis force is 0 when the partial is stationary. And when the partial is in motion, Coriolis Force is directly proportional to the partial's velocity. We basically said that in the last slide. And then air partials are deflected to the right in the northern hemisphere. Wind forces. All right, pressure gradient force. Pressure gradient force is defined as the delta P over delta N, always measured perpendicular to the isobars. Okay, I think I got some example pictures next. If I not, we'll go over to the charts. Always measured perpendicular. High pressure change over short distances is a high pressure gradient. Air is forced to respond in order to fill the void. Contour gradient force, delta Z over delta N, is a measure of pressure gradient force on upper air charts. So like I said, upper air charts are different because you have constant heights. On the surface, you have constant pressure. So it's kind of a way to look at it a little bit different. So you have contour gradient force, how far apart are the contours on the upper level charts. Pressure gradient force is how far apart are the isobars, the lines of equal pressure. So that's the difference between the surface and upper air. Okay, so here, pressure gradient force, the closer those lines are together, the stronger the pressure gradient force. So you're measuring perpendicular to the isobars, and the closer together, the more intense the pressure gradient force. Contour gradient force, same thing. You're measuring perpendicular to the contours, and the closer they are together, the stronger the contour gradient force. Geostrophic wind. It's an imaginary wind that would result if pressure gradient force, Coriolis force were in exact balance, which they never are, but perfect atmosphere, everything's perfect, that would be a geostrophic wind. Now, calculated by analyzing pressure and contour gradient while taking latitude into account, and assume straight line flow with no centrifugal force and no friction. So you're above the boundary layer, no friction. This is like the perfect wind. There is a chart for this. I don't think I put it on here. There is a geostrophic wind chart. So depending on what latitude you're at, how far away apart your contours are or your isobars are, your geostrophic wind can be measured with that chart. And that's like I said, that's a perfect scenario. But if you're close to the surface, below that boundary layer, you're pretty much going to have friction. You're always going to you'll have Coriolis force, as the Earth rotates, causing that. You'll have centrifugal force, and any curvature on an air parcel will create centrifugal force. So now you got another force you got to take into account. Like I said, everything's in balance. Pressure gradient force, Coriolis force, now you got a straight line flow. That's on your surface chart. Contour gradient force, Coriolis force, there's your straight line flow on a constant pressure chart. Will not curve. Nothing. The pressure gradient force and the contour and the Coriolis force are in balance with each other, so there's no curvature in that wind. Supergeostrophic wind. Actual wind is faster than the geostrophic wind. Coriolis force becomes dominant and forces the air to flow to higher heights, loses kinetic energy until the velocity slows down. The Coriolis force subsides. Okay, until velocity slows down and Coriolis force subsides. Found in anticyclonic curved flow, that is a high pressure system where Coriolis force must balance both pressure gradient force and centrifugal force. Alright, I think there's an example on this one. Yeah, I don't have it. Maybe in the next couple slides. Let's go through this. Subgeostrophic wind. That's an actual wind that's slower than the geostrophic wind. So now your geostrophic wind's that perfect wind, so this is slower than that. Pressure gradient force becomes dominant and forces the air to flow toward lower heights, gains kinetic energy. So now you're flowing toward lower heights, so you're going downhill, so you gain kinetic energy. The other one was flowing to higher heights, so you're going uphill, so you're losing kinetic energy. Until the velocity speeds up or Coriolis force becomes more dominant. It's found in cyclonically curved flow, which is a low pressure system around the low, where the Coriolis force and the centrifugal force act together to balance pressure gradient force. We will have some charts on this. Okay. Sub or supergeostrophic winds. Supergeostrophic flow. You can see the curvature here clockwise around the high. There's high pressure to the south. Supergeostrophic. So now you got that curvature. That is where that's found. You actually gain speed because you're actually going toward higher heights, so velocity increases. Kinetic energy increases. All right, round the low, now you have cyclonic flow, and that is counterclockwise around the low. There would be a low to the north. So now you're going uphill, so you lose kinetic energy on a subgeostrophic wind. All right, gradient wind. Gradient wind would result if there were a balance between pressure gradient force, Coriolis force, and centrifugal force. It assumes no friction. So I got a couple typos there. Whatever. No friction. Gradient wind is a result where there's a balance between pressure gradient force, Coriolis force. Everything's balanced. So you pretty much, no friction, you have a straight flow wind. So when you do have friction, you have wind flowing, then you hit that friction, your winds are going to actually slow down and they're going to back. They're going to back is going to go counterclockwise, so they're going to shift in toward that lower pressure. So winds flow into a low, they flow out of a high. So if we had that anticyclonic curvature, which you don't see any curvature here, but if there was a high pressure system, then it would flow the other way, but it would still, that friction would still try to bring it out of the high, even though the high most likely would overcome that and still flow into a high. So actually flow out of a high because your low or high pressure air is downward vertical motion, spins clockwise and flows out of the high because you have low level divergence. From throwing words at you, you don't understand. We'll get into that stuff here, maybe on this video. I'm not sure. Maybe on the next one. Somewhere throughout this course, you'll understand divergence, convergence, confluence, difluence. That terminology. So right now, we just need a perfect wind. Everything's balanced, straight line. Add friction in that. So friction always slows you down. So the winds are going to back. Cyclostrophic wind. Didn't know there's so many winds, did you? So any type of curved flow adds another force, centrifugal force. The apparent force that deflects an object away from the center of rotation, the centrifugal force. Direct outwards from the axis and is perpendicular to the direction of velocity. Centrifugal force preserves the circulation. Centrifugal force begins to resist the pressure gradient force. And the example is for a hurricane or typhoon. So, I guess the example hurricane or typhoon would be counterclockwise. Now you're trying to force that one out, but here you got a low pressure system. Let me get on a whiteboard here, see if I can draw this for you a little bit, give you a visual. Go to the next slide. We got vorticity. So we don't have a visual. Let me get you a visual real quick. So a low pressure system is red. So here's a hurricane. Low pressure system, tight gradient force. Okay, now when you start to spin, going counterclockwise, it wants to push that force out from the center. That's centrifugal force. Low pressure is an upward vertical motion. So coming out of the center of the low. So you have the force flowing in to the low. So winds will flow counterclockwise and into a low. So now you have this outward force going against that pressure gradient force. So the centrifugal force preserves the circulation because it's an outward force. So it's helping that circulation. Starts to push against the pressure gradient force and resists that pressure on the inward flow. So that's what it's saying as far as cyclostrophic wind. Perfect example is a hurricane. So centrifugal force preserves the circulation. The force begins to resist the pressure gradient force because it's in the opposite direction on a low pressure system. So cyclostrophic wind. Now, I don't think this is in here. I haven't covered that. There is one other force, a centripetal force. It's a force into the center. You will have that on a high pressure system. We don't really cover that as a wind. High pressure pretty much dominates your downward vertical motion, outward flow from the high. The density is too strong to be worried about a centripetal force that would actually push toward the center of that high to try to bring that force back in. So vorticity, very important. Like we said, 500 millibars is our chart that's going to measure vorticity. You can measure vorticity at any chart, but if the National Weather Service used to put out vorticity charts, they were always 500 millibars. That's your mid layer there. That if you have any significant upward vertical motion or rotation, you'll find it on that chart, and that 500 millibar chart, cutting that atmosphere in half, will show you the significance of what's happening with that low pressure system, where your positive vorticity advection is happening, negative vorticity advection is happening, and then you can see upward and downward vertical motions to determine, is that low getting stronger, is that low deepening or filling, or is that high weakening or building. That's terminology for highs and lows. So measured in radians per second. Created by shear, curvature, or both. Vorticity is vertical in meteorology unless otherwise specified. So anytime you hear vorticity, it is in the vertical. If you hear that on the charts, it's in the vertical. That's what you're looking for with vorticity. You're looking for shear, curvature, or both. Vertical forms of vorticity include whirlpools and merry-go-rounds. Think about the rotation. It is actual. You think of horizontal, but it's actually vertical. Because of your rotation, it's like a vortex. Horizontal vorticity is limited to evaluating shear through a layer, and then forecasting severe storms, turbulence, and cloud patterns. So if you're looking for shear through a layer, you're looking at, like, say, pull up a couple charts, or you're going to have to pretty much pull up a SCOOT chart, and you're going to look for but that's going to be your vertical shear. You're actually going to pull up one contour chart, and you'll look at different wind speeds. Okay, but let's pull that up real quick. We can give you an example of that. Let's go to alright, the colors are going to kind of clash on this because I have this radar I have a chart overlaid on radar, so it's going to kind of clash a little bit, but you'll see, you'll still get the point. Now, we want to throw maybe, it's going to be pretty much 850. So our areas of low level wind shear, or this is showing our areas here. So in color, now we're going to throw our radio sound data here. All right, maybe I should take that color off because we're just kind of cluttering everything up. It's getting a little bit hard to see, but you can see it in this area. You can see that shear. Let's just erase this real quick. Throw the station plots up there. Just throw those the radio sound data. Now here we got 45 knots. It's 45 knots. Nothing really there for shear. 45 knots to 30 knots. I mean, you can say, okay, this wind is passing this wind, so you have wind shear in that area. So you got low level wind shear. 30 knots going into 25. You're just going to catch up with that. So you got a little bit of wind shear there. Nothing real significant, but you got 35 knots here, 25. You got a little bit of wind shear there. So we've seen that area of low level wind shear. So that is going to be, at any given layer, it's going to be your horizontal vorticity. So you can look at rotation, like right here's a wind shift right here. That's upper level. I wouldn't really call that a front, but maybe some troughing, definitely some rotation. So your horizontal is your, basically it limits you to the shear at a certain layer. But for forecasting severe storms, you want to go to the 850, look for low level wind shear. If you have a 45 knot wind, that's basically is classified as a low level jet. So this is low level wind shear, low level jet, anything significant weather that pops up in this area, which we know we're dry here. We're in that heat wave. We're real dry right here. If we had the moisture and the instability to go with that, you could actually have tornadoes in this area. So Texas to Oklahoma. So that's what you're looking for evaluating shear at a certain layer. Okay, let's get to back to the class. Let's go. Here's a vorticity chart. We did create one of those. So positive vorticity. There's an X that's marked with an X. Any advection, which I don't see any major advection here, but it does show there's a positive there, positive here. So you got a little bit of positive advection there, but I don't even really see that. They've colored this in pretty strong. I mean, on this chart, honestly, I don't see a lot of actual positive vorticity. This is several days old, so it doesn't match the charts we've been looking at for today. This is just an example of a vorticity chart. So the area's upper level divergence or rotation in the atmosphere is located on this chart. This is one I create with the software that I have, so you probably won't see this out there anywhere.